Hello everyone, welcome to the next lecture on the multivariate normal distribution. Today we will see how we can calculate the moment generating function. Myself Dr. Harish Garg. You can follow my YouTube channel where you can find the playlist of applied multivariate analysis, and you can see the last lecture was on the bivariate, multivariate, transformation, independent random variable, marginal density function, conditional distribution, and many more lectures in this playlist. You can subscribe my YouTube channel so that you can get the notification in advance when I upload new lectures related to this topic. So what we have discussed is when x follows my multivariate normal distribution whose dimension is p, that means x1 is my x here, and each of the xi's follows the normal distribution with the mean mu and positive covariance matrix sigma. For more detail about this lecture, you can listen this lecture so that you can understand the today's lecture very well. The moment generating function is denoted by mx. T is a variable which is defined like this manner: expected value of e raised to power t transpose x. Remember, T is my p cross 1 matrix. That means T is my T1, T2 and up to the Tp. That is the dimension. X is also my p cross 1 matrix. So therefore, what is the value of the T transpose? It is 1 cross p. Then what is the T transpose into X? If you multiply them, it is 1 cross 1 matrix. Now based on this definition, your target is to compute the moment generating function of this multivariate normal distribution. And our target is to prove this result. It's a very simple result. I will explain you, but before that, let me quickly explain you the concept of this result. If Z is my multivariate normal distribution, Z1, Zp, such that each of the Zi will follows the normal distribution 0, 1 and they are independent. This is the meaning of this first line. Fine. Then your target is to prove the moment generating function of this result. The proof is very simple. You can see from here what is the meaning of this case. Normal distribution 0, 1. That means it's a univariate standard normal distribution. Fine. Once it's a univariate, then we all know moment generating function of this, that is e raised to power ti square divided by 2 corresponding to the each of this I. Then they are independent. What is the property of the independent? I can take the product and hence prove this result. Now let's see how you can prove in a systematic way. So once Zi is my univariate normal distribution, by the definition of the m.g.f, we can define the moment generating function by this manner. Now by using the independence of this, we can define this is product of moment generating function. So I can substitute this value. What is the moment generating function is e raised to power ti square divided by 2. So it's a product. I can return this quantity as ti square divided by 2. Fine. Now because t is my vector of p, that is t is my p cross 1. What is the t dash? It's a 1 cross p. So therefore t dash into t is 1 cross p, and we can return ti square to be t transpose into t. Fine. So I can replace this summation value. Fine. Because if you say t is my t1 and tp, and what is the t transpose? t1 up to tp. So what is the value of t transpose into t? That is a t1 square, t2 square and so on. So I can write this summation part to be exponential of t transpose, and that's the required result. Now based on this property, I can start with the moment generating function of this. What is given to you? It is given that x follows my multivariate normal distribution, this value. What does it mean? What is the definition of the multivariate normal distribution? X follows my mu plus a z. Fine. Where this z follows multivariate normal distribution with the identity with the parameters 0 and I, and they are independent. What is the property of this a? This a is my non-singular matrix, fine, such that A into A transpose is my positive covariance matrix. That's the definition of the multivariate normal distribution. Now let's start with the definition of this moment generating function. I can substitute the value of the x from this equation into here. Now I can write this value as E of T transpose into mu, E of T transpose A of Z. I can return T transpose of mu is a constant value which is outside, because we all know E of AX will be A times expected value of x, and this value I can return in terms of this. Can you write by using the property? What is the AB transpose? B transpose A transpose. So can I write this quantity as A transpose into T? Fine. Now that means this is written this manner. Now if you look about that, this result, what does it means? It is e raised to power this. This is again the moment generating functions of the parameter z. What is the t? This is my parameter, because you can see what is the definition of this t transpose x. Now in this case x will be my z, capital small t will be my A transpose T. Now what is the moment generating function of this parameter? What is the moment generating function of the Z? What is my Z? Z is the normal distribution with 0, 1. By the previous result, this will be T transpose T divided by 2. So I can substitute here. Again I can use the property, that is mu transpose. This will be transpose A transpose. Transpose of transpose is my 1, that is A, which comes to be this quantity. Now what is the value of A into A transpose? A into A transpose is sigma, so this number will be my T transpose E of half T transpose sigma of T. Now you can add them, you will get the same expression of this result, and that's the derivation of the moment generating function. Second result, if x follows the normal distribution, then the moment generating function of x minus mu comes to be this number. This is given to you, fine. Now as x follows my multivariate normal distribution of this, what does it implies? X minus mu will follows normal distribution with the mean 0, variance this, fine. Now this also follows the multivariate normal distribution. What does it means? The mu will be my 0. So I can substitute the value of the mu at here. You will get the required result of this expression. Now let's see one example. If x follows n2, what is the meaning of that? X will be my x1 and x2, where mu is my this and sigma will be my here. Then find the moment generating function of x. Now what is the dimension of this? There are the 2 dimensions, so I can see capital small t will also my t1 t2. So therefore what is the definition of the moment generating function? This is e raised to power t transpose mu plus half this value. So I can substitute this quantity. What is that? T transpose into mu, that is T1, this is my T1, T2. What is the mu? Mu is my 2, 3. So what is the answer of this? When you multiply them, 2T1 plus 3T2. So this is the value of this. Now for the second number, T transpose sigma of T. So this is T1, T2. Sigma will be 2, 1, 1, 2, and this will be T1, T2. So how you can multiply them is a T1 of T2. This will be 2T1 plus T2, 1T1 plus 2 times this. Now you can multiply them, 2T1 square plus T1 T2 plus T2 T1 plus 2 times T2 square. So I can substitute this value at this point. Or you can write it directly, because this is a twice t1 square, twice t2 square, and addition of this value 1 plus 1 is twice. Now that 2 will be cancelled out, and that is the expression of this moment generating function. Now once we know the moment generating function is there, how you can find the moments? Recall that if you have the x is the univariate normal distribution, how you can find the expected value of the x from the moment generating function? We take the first derivative at t is equal to 0. How you can find the x square? That means the second derivative of the moment generating function at t is equal to 0. The same way how you can calculate this value, because it's a multivariate normal distribution, how you can correlate the moments, that is the mean, variance, covariance, with the help of the m.g.f. So that's very simple. Let's say k1, k2, kp are the non-negative integers. What is the meaning of that? If I have k1 square, k2 for example, then the value of the k1 is 2, value of the k2 is 1, and so on. Now if k1, k2, kp are the non-negative integers such that their sum will be my k. So what is the k in this particular example is 3. Then we can start from the partial derivative. So I can substitute the moment generating function. By the definition it comes to be this number. Now e I can taken is outside, it's come to be this value. Now look at that. How you can take, firstly I can take the partial derivative with respect to p. So that means only this component, fine, it will be e raised to power, what is the derivative of this? That's xp e raised to power tp into xp, fine. If you take the second derivative with respect to p of this quantity, it will be xp square of e raised to power tp into xp, fine. And if you take the kth derivative kp, if you take the kpth derivative, it will be power of kp, fine. Similarly, if you take t2, that is my here, and you can substitute this value, you can get this number. You can see xp raised to power kp, fine, and this quantity is my same, fine. Similarly, if you take with respect to t1, it will be x1 raised to power k1, and so. Now what is this value? This is a constant value which can be written outside. Now you can substitute t is equal to 0. This value will be 1. So the left hand side will be my this expression at t is equal to 0. I will explain you with the help of example. Like here, how you can find that? It is my partial derivative with respect to t1 one time, partial derivative t2 with respect to one time. So it's a double, it's a 2 at t is equal to 0. How you can define this? Partial derivative of t1, partial derivative of t2 2 times. Now the total is my 3 of mxt. Similarly, this will be partial derivative t1 square, partial derivative t2 square of 4 times mxt. Now I will explain you this concept with the help of the numerical example. I have considered the same example. How you can find this number? You have to find this by using moment generating function. Otherwise, how you can find this without using m.g.f? That is very easy, because you can use the covariance. What is the covariance of x1 x2? That is e of x1 x2 minus ex1 ex2. What is the covariance of x1 x2? That is 1. This value we need to calculate. What is the expected value of x1? 2. This is my 3. So can you find this number? It will be 6 plus 1, 7 is the, this is without using the m.g.f. But how you can find using the m.g.f? That's very simple. Your target is to find this value at the point t is equal to 0. So it means your first target is to find the this number. And this is the same example as I have considered previously. I can start from here, substitute the value of the mu at this point, capital T at this point, sigma, and all these values. You will get this moment generating function. Now I can partial derivative this firstly with respect to T2. So exponential part is always the same, 3T2 plus T1 square plus T2 square plus into derivative of this component, that's with respect to T2, that's a 3 plus T2 plus T1. Fine. Now you need to find the second derivative. Now you have to find this with respect to T1. So you have to apply the product rule. This is the first function, this is the second function. So how you can define that? That is the first function, derivative of this with respect to T1, this is 1, plus this function, derivative of this into this part. This is the derivative with respect to. Now you can substitute at t is equal to 0. What is the value of the left hand side? This is x1, x2. This is e raised to power 0 into 1. This is e raised to power 0. This is 3. This is 2. So what is the answer of this? 1 plus 6, 7 is the right answer of the problem. So you can see the same result we have obtained without the m.g.f. and with m.g.f. So now look at the second example. Again I have considered same data, and you have to find the expected value of this by using with the m.g.f. So what is the definition of this in terms of the moment generating function? Because it's a x1 square, that means t1 square, and x2 is a single, it's my t2. Now the total quantity is 3, so it is a 3 times derivative. Now as we have defined, this is the moment generating function of this expression, you can find again it is my this number. Now find, because how you can define this quantity, let me quickly say, it is my this number. Firstly you have to find, let me firstly clear it, you have to firstly find this value of the moment generating function, then you have to find this number of this quantity, and then you have to find again with respect to t1 square. Fine. This is the way you can obtain that. Now this value we have already obtained in our previous step, that is my this case. Fine. Or if you want to derive this result similar in this example, you can do it, and we have obtained this expression. Now I can again differentiate this with respect to t1, so it is my cube. How you can differentiate this t1? It's a product rule. It's my first function, it is my second function. So what is the derivative of this? I can take the first function as such, t1 plus 3t2 plus t1 square plus t2 square plus t1 t2 into derivative of u, that is my twice 2t1 is a 0 plus t2, that is the derivative of u, into this value of v, plus I can take this expression of u and derivative of v. How you can derivative this with respect to the t1? So 1 will be 0, again it's a product rule, so it will be 3 plus this into derivative of this is my 2, plus derivative of this with respect to t1 is 1 plus 2 times this value. Fine. This is the function values of this quantity. Now you can substitute the value at t is equal to 0. What is the value of this? So left hand side will be my expected value of x1 square into x2. So this will be e raised to power 0, 0, 0, 0 and 0. That means e raised to power 0. This will be my 3. It is my 2. That's a 6. It is my 4. Plus e raised to power 0, 0, 0 and 0 into 2 into 1 plus it comes to be the 3, it comes to be the 2, that's 6. So what is the answer of this? E raised to power 0 is 1 plus is a 7, 7 to 14. So the right answer of this problem is 24 is my right answer of this problem. So this is the way you can find the moment generating functions and its movement in a simple manner. I hope you can like my video so that I can understand it. You can well read this lecture in simple way. We will see the next lecture on some properties of the m.g.f. Till then, you can like, share and comment on my videos. Best of luck students. Happy learning.